करना है, we want to just move on to A-levels equilibrium. But since most of it is based on your AS, KC, and KV, so we have to do that again. So iska to khair obvious hai ki they're asking for the units of KC. We just did one type. We did two types of questions. One is that they're going to ask you about the expression. So it's product concentration. The exponent becomes the power divided by the reactant concentration. So it's going to be NH3 squared, or मेरे ख्याल से ये वाला होगा NH3 squared and N2 and H2, and that's going to be cubed. Or plus this, there has to be a multiplication. So that's one. अच्छा, ये वो question आ गया. We were doing questions related to calculating Kc. You have to find what the equilibrium constant Kc is. So for example, I've got this reaction where I have, so the reaction is given H2 and I2, and they are in equilibrium and they're producing 2HI. You have your initial concentration, you have your equilibrium concentration. So the initial concentration that's given over here, that's kitna hai? 2 moles of, you're given 2 moles of hydrogen. You're given 3 moles of iodine, and they were heated together. So uska matlab hai, you're not given any moles of HI. Okay, that is not given. So those are your initial moles. Up here, you're saying the container had a fixed volume of 1 dm cube. That would be helpful because concentration is moles over volume. So if the volume is 1 dm cube, the concentration is going to be exactly the same. ये चीज याद रखना कि KC के अंदर you always use concentration. You don't use moles. So which is why they gave it 1 dm cube, but it would still mean the same thing. At equilibrium, there were 2.4 moles of iodine. So at equilibrium, you had 2.4 moles of iodine. Now, what that indicates is that you started off with 3 moles, and now you have 2.4 moles. That means 0.6 moles is missing. And that means 0.6 moles probably reacted. Okay, that's why they're not there. So the ratio is going to be applied to this. You can remember you 1:1:2. That ratio only applies to the amount that is reacting or that is getting produced. It does not apply to the initial moles. They could be present in any quantity. It doesn't apply to the equilibrium moles. They would also be present in any amount. So 0.6 reacted, so it's 1:1. So that means 0.6 of H2 would also react. And if 0.6 H2 is reacting and it's reacting with 0.6 I2, so दूसरी side पे it's going to be double. So 1.2 moles of HI would be produced. So your equilibrium moles are going to be that you started off at 2.6 reacted, so you're left with how much? You're left with 1.4 moles. You started off with 0 and now 1.2 got produced, so your moles would be 1.2. If it's getting reacted, that means they're going to be less. If they're getting produced, they're going to be more. Okay, so you found your equilibrium moles. The concentration would be exactly the same because it's 1 dm cube. And your Kc expression would be HI concentration, that's going to be 1.2 squared divided by the concentration of H2, which is 1.4 times 2 times 2.4. So what do we get? Calculator, okay, what's the answer to that? That's 1.2 squared. So very quickly, it's 1.2 times 1.2. And I'm going to divide that by 1.4. Divided by 2.4. So I'm getting something that's close to that's exactly 0.429, which is C. So that is what you're going to get. Since we're doing Kc, I'm going to add some points over here. Kc can now remember concentration is used in Kc. So keep this in mind that like concentration is what is used in Kc. And remember, for solids, the concentration is always equal to 1. It's taken as a constant. 1 ka matlab you don't actually You don't actually write Kc over there. And if something is in large excess, that means if you add too much of something, its concentration would also be considered to be constant. So normally, if you have water as a present in an equation, so if water is in a reaction, and the solution is aqueous. So what you do is that water would be taken as its concentration would be taken as one as well because it's going to be in large excess. I'm just going to explain what large excess. I mean, what large excess means is that if you have a solution, for example, you've got NaOH and you've got HCl, and they are reacting together. बल्कि एक reaction लिख लेते हैं कि just to give you an idea that if I have ethanoic acid reacting with water and it's in equilibrium with CH3CO minus one ions and H3O plus one ions, and all of them happen to be aqueous. Okay, so all of them they happen to be aqueous. Water would be written as liquid. This is aqueous and this is aqueous. So the Kc expression for this particular reaction, you're not going to write water in the expression because water, because everything is aqueous. That means this the whole solution is made up of water. There might be a few particles of ethanoic acid. There might be a few particles of ethanoic ions. There might be a few particles of H3O plus one. But overall, by and large, the entire thing is actually the whole solution is actually water, right? So that means water is in large excess. So for example, if this is 0.1 moles, water might be 5 moles. And let's say this is 0.1 moles and this is also 0.1 moles. So if the concentration of ethanoic acid decreases by a tiny amount, let's say it goes to 0.08 moles. So it decreases by a tiny amount, 20%. It decreases by 20%, which is not a tiny amount. It decreases almost by 0.02 moles. So water moles would almost still remain almost the same. If this is decreasing by 0.02, so if this decreases by 0.02 and this also decreases by 0.02, well, in the case of ethanoic acid, the concentration has significantly decreased by 20%. But in the case of water, which is in large excess, that means there's too much of water in the whole solution. Its moles barely decreased by a very, very tiny amount. Okay, there's almost negligible change. So it decreases by 0.02 as well. But it's almost going to be constant. There's hardly any change, hardly any noticeable change overall. Percentage wise, that's a very, very tiny change. So remember this, any reactant or product, if it's in large excess, its concentration can be considered to be constant and it would be taken as one. Okay, is this tiny point clear? ये solid का तो वैसे ही मान है क्योंकि solids, the term concentration does not apply to solids. Clear ये? Minil, is this clear? Qasim, Hala, Mesa, is this clear?
Yes.
अच्छा, so since we are doing Kc, I'm going to add another tiny point over here, which is Kc always uses concentration except case wale ke andar, the first thing that we wrote concentration is used in Kc. Kc can use moles directly only under certain circumstances. only when Kc has no units. Otherwise, it's always always going to be concentration. And let me explain. For example, H2, the H2 and I2 reaction, you've got this 2HI. In this case, Kc will not have a unit. It's going to be HI concentration squared divided by H2 times I2. So if let's say at equilibrium, they have a certain amount of moles, zero point 0.2 moles, this is zero point 0.2 moles, and this is zero point 0.1 moles, right? The point is, I don't need to convert them into concentration in this particular case because it's got no units. You get the numerator terms and the denominator terms would cancel out. So let's say even if the volume is 2 dm cube, it doesn't really matter what the volume is in this case because the concentration of the numerator would be 0.1 divided by 2 mole per dm cube squared divided by H2 would be zero point 0.2 moles divided by the volume is 2 dm cube and I2 is also zero point 0.2 divided by the volume which is 2 dm cube. Now what happens is if the number of terms in the numerator and the denominator are equal, तो इस 2 का कोई फायदा नहीं है because the 2 will because there are equal number of 2's present in the numerator and equal number of 2's present in the denominator, so they're going to get cancelled out. So this thing is not really required, but this is only an exception. You can use moles for Kc only in this case, which is that the units, it doesn't have a unit, it's got equal number of terms in the numerator and denominator, so dividing by the volume to get concentration, that would be a useless task. Okay, because all the 2's are going to get cancelled anyways. But if Kc has a unit, and the number of terms in the numerator and the number of terms in the denominator are not equal, in that particular case, the volume must at all costs be incorporated. You always have to, you can't use moles directly, you always have to find out concentration. The reason I'm telling you this is because a lot of people, simply when they find moles, they just plug it into the Kc expression. Make sure it's always you have to find concentration. Only this is the only case where there's an exception. You don't really have to find concentration. Okay? So going back to our question, which is the next question. So here's another one, which is exactly the same. You're going to have. Sorry, मैं disconnect हो गया. एक second. चलो वापस उस पे ना वर्कशीट की थी हमारी so one more H2 plus I2 and again forming 2HI. You've got your initial moles which are given. TK, the moles are given. That's 0.2 moles. This is 0.2 moles, 0.15 moles. TK top in, and they've written down the initial moles, and they're heated together, so there is no moles of HI. TK, that is not there. And your equilibrium moles are, at equilibrium, he found out that there is 0.26 moles of HI. So that means you started off with 0 and now you have 0.26. So that means how much got produced? You got 0.26 got produced during the reaction while equilibrium was being set up. And so what is the ratio? If 2 get produced, one of I2 would react and one of H2 would react. So it's 2:1. So if 0.26 are getting produced, so half of that would react on the other side. So 0.13 and 0.13 on this side would react. So ये clear है कि 0.26 got produced. You had 0 and now you have 0.26. And according to the ratio, 0.26, 0.13 and 0.13 will react. So out of 0.15, 0.13 reacted, so you're left with how many moles? 0.0 0.15 minus 0.13 कितना होता है? That's 0.02. And out of zero point 0.2 moles, your starting moles 0.13 reacted, so you're left with 0.07 moles as well. So you found your equivalent moles now, and you just have to find Kc. Achha, यहाँ पे you would notice that it did not give us volume. Okay, the reason they did not give us volume was that Kc over here has no units. So in that case, you don't need volume. You don't need to find concentration. You can put moles directly into the equation. So it's Hi squared. So it's 0.26 squared divided by 0.07 times 0.02. So that's Kc. अच्छा ये एक और question है which is slightly I guess more difficult, more tricky. This one is that you have two reactions, and they're asking that the the numerical value of Kc for reaction 1 is 2. So for reaction number 1, the Kc has already been calculated. It is given as 2. Okay, that is already given. And they're asking, based on this, under the same condition, what is the numerical value of Kc for reaction number 2? So you have to find the numerical value for reaction number 2. Now, what you're going to notice, or you might not have noticed, is that if you look carefully, the two reactions are exactly the same. I mean, there's absolutely no difference between the two reactions. They're just written differently and they are balanced differently. इसमें क्या है, on one side you have X2Y gas. You also have X2Y gas in the other reaction. And that X2Y gas is in equilibrium with what? It's in equilibrium with X2 gas and Y2 gas. In the other equation, the X2Y gas is also in equilibrium with X2 gas and Y2 gas. So they're exactly the same reaction, but written the other way around. Okay, so remember that in equilibrium reactions, it doesn't really matter. I mean, there's no, in reality, there is no reactant or there is no product. I mean, you can switch them around. It's basically two things in equilibrium with each other. I mean, you can write them in the other, you can write them in the other way around as well. That doesn't make a difference. But what it would do is that it will change the expression for Kc. And if the expression for Kc changes, the value of Kc would also change. So, plus they are balanced differently as well. Okay. Over here, Y2 is half. Basically, the first equation balancing is divided by 2. That X2Y was 2, over here it's 1. X2 was 2, over here it's 1. Y2 was 1, over here it's half. So it's basically divided by 2. So the balancing is different as well. So the two reactions are exactly the same. That means the reactant concentrations are going to be exactly the same as well because they are exactly the same reaction. So the Kc expression for the first one is, it's going to be X2Y concentration, and that's going to be squared, divided by X2 concentration, and that's going to be squared as well, and times the reactant concentration, which is Y2. So that's my first reaction Kc. The second reaction Kc is that the product, because it's written the other way around, it's X2. And Y2, the power would be half, which is under root, and divided by X2Y. So you've got these two expressions, and remember, they are exactly the same reaction. Now, if the first expression has a value of 2, what would be the value for the second reaction? The first thing is that since they're the same reaction, the concentrations are going to be exactly the same because they are exactly the same reaction, except written differently. So what operation needs to be carried out to convert, I mean, what's the difference between the two? The first difference is that X2 and Y2 were in the denominator over here, and in this one, X2 and Y2 are in the numerator. So one thing is that it's upside down. It's the whole expression is upside down. So over here, if the above one is 2, over here it's going to be 1 by 2 because it's written the other way around. The other major difference is that over there the powers are squared. Over here the power is 1. That means it's being under rooted. X2 is squared. Over here, the power is 1. That means it's again underrooted. Y2 was power 1. Over here, Y2 is power half. So that means all the terms are getting underrooted as well. So this 1 by 2 would be underrooted as well. Okay, because it's the same expression. So I carried out that the first thing was that the values are written. I mean, the numerator becomes the denominator in the other expression. So everything is upside down. So over there it's 2, over here it's 1 by 2. And everything is being underrooted, which means that मतलब वो नजर आ रहा है कि everything is, it's got 1 less power. ठीक है. So it's 1 by 2 under root, and that's going to be my answer. ये वाला clear है? Is this clear, Hara? Ramesa, Minal, Qasim, is this clear?
Yes.
Yes, sir.
Yes, sir.
चलो ठीक है, एक दूसरा बस केसी का फिर कर लेते हैं. I'm not going to do a lot of questions. बाकी तो फिर A levels में करेंगे. The other KC was that the other type of question would be that your KC would be known, and you have to find equilibrium concentration, mostly the equilibrium concentration. So that's the third type of question that you get on KC. So वो क्या होता है? So for example, you're given what you're given the initial moles. I'm not going to write the question. I'm just going to, let's use the same equation. So you're given this, and your initial moles are 0.1. This is, let's say, 0.2, and this is 0.15 moles. Okay. And because you've got equal number of terms in the numerator and denominator, you don't need to find concentration in this case. So the equilibrium is completely unknown. You have no idea. They did not give us any information about what the equilibrium moles are. So we don't know any idea. So that is what we're going to find. So no information is given apart from the fact that initial moles are given. And they gave us the Kc value, which is, let's say it's 1.2. Okay, so they gave us Kc. So what needs to be done is that, how would you solve this? So the issue is that you don't know how many moles are getting produced or reacted on either side. So you have no idea. So you're going to make an assumption. Well, your starting moles are 0.1 for H2. And we don't know what happened to it. We don't know whether they increased. Maybe the equilibrium was established and the whole reaction shifted backwards, right? So it would increase. Or maybe the equilibrium shifted forward and the whole equilibrium got established in the forward direction. And in that case, it would be less than 0.1. But at the moment, I have no idea what it is. So I'm going to assume that X moles reacted. क्योंकि value तो है नहीं मेरे पास. I don't know how many moles reacted, so I'm just going to use X. So since it's 1:1, so if X moles are reacting, so X moles of I2 would also react. And if one reacts with one, so in the product side, 2 would be produced. So if X reacts with X, on the other side, 2X would be produced. So since I don't know what amount is being reacted or produced, I just used X. Now, based in terms of X, I'm going to figure out the equilibrium moles, which are going to be, maybe you started off with 0.1 and X of them reacted. So that means you have 0.1 and X are gone. So that means you have 0.1 minus X. I2 के क्या? You start off at 0.2 and X moles reacted. अच्छा, इसको ना 0.2 को initial moles I'm going to change it to 0.1 because in the syllabus they are very specific that quadratic equations will not be, they're not going to ask you to solve quadratic equations, so I just simplified it a little bit. So I2 is 0.1 moles and X are reacting, so you're left with 0.1 minus X. On the other side, you have 0.15. And इसको भी, just to simplify, like my calculation simple. Initial moles, I'm going to take it as 0. Again, just to be careful that we don't have to solve quadratic equations. So your starting moles are 0 and 2x got produced. So the moles over here would be 2x. So I have my equilibrium moles in terms of x. My expression would be 2x squared. That's hi squared divided by 0.1 minus x squared, or 0.1 minus x into 0.1 minus x. Okay, so it's product over reactants. The Kc value is 1.2, and we're going to try and solve this. Okay. As the reason I had to change the values was they are very specific about not solving quadratic equation. So we're going to under root this on both sides. So I'm going to get, what am I going to get over here? It's going to be 2x.1 minus x at the bottom. On the other side, I'm going to get either plus 1.2 under root. You can under root me, you're going to get two values. Or the other one would be minus 1.2 under root. Okay, so we're going to solve for two situations. So 2x, and if I take 0.1 minus x, I'm solving for this one. So it's going to be 0.1 times point times d. So this thing goes on the other side, so it's going to be 0.1 into 1.2 under root. And then it's going to be minus x times 1.2 under root. Then we're going to gather all the x's, so it's going to be 2x. And it's going to be plus x times 1.2 under root on one side. On the other side, I'm going to have 0.1 times 1.2 under root. I'm going to write the expression, solve it. So taking x common, so 0.1 times 1.2 under root, and the niche kya, that's going to be 2 plus 1.2 under root. Let's go detail में solve कर लें, ठीक है. This is what you're going to get for plus 1.2 under root. For minus, so that's my x1. And I can solve for the other one. But the only thing I'm going to do is I'm going to use the same expression, except 1.2 under root, I'm going to substitute 1.2 under root with minus 1.2 under root. So if I do that, what do I get? I get ऊपर वाला minus हो जाएगा because 1.2 under root, I'm using the negative value. And the bottom one would be 2 minus 1.2 under root. Okay, so the only thing I did was, okay, the final expression I got for this one, I just switched 1.2 under root with minus 1.2 under root. So I'm going to get two values for x, which is going to be x1 and x2. Binal, calculator है आपके पास?
Yes.
ये solve करके बताओ ना कि क्या, what do you get for this?
Minus 0.121.
You put minus 0.
121.
Then the second one is
Minus 0.0353.
the minus 0.0353. So you get two values, but only one of them is going to work. Okay, which one is going to work? You're going to go back to your table. Okay, किधर गया हमारा table? ये तो. So you're going to go back to your table, and दोनों minus क्यों आ रही है? इसमें हमने कोई गलती नहीं की. I'm going to tell you, you're going to go back to your table, you're going to find the moles. The moles that you get at equilibrium, they cannot have negative values. Okay? So in this case, we are getting a negative value. So दोबारा double check and let me try and solve this as well. ऊपर math कोई देख ले कि did we do the right math? It's 2x squared, 0.1 minus x squared. वो तो वही था, 0.1 minus x, 0.1 minus x, and 0 plus 2x, yeah. Did I do the correct math? I took the under root, 1.2 under root. What else? Just double checking 2x. Okay, you got 2x, 0.1 minus 0.1 into 1.2 minus x into 1.2. So that looks fine. The x went to the other side, so that's this. 0.1 times 1.2 under root and took x common, so that's 2 plus 1.2 under root and went it divided on the other side. How middle how could the first value be negative? Is this
You have to switch the values. मैंने 0.0353 is for the first equation.
and it's positive, right?
Oh yes, now it's positive.
But you see the other one was negative, right?
Yes.
Acha, theek hai. Theek hai, that makes sense. Acha, so this one will not be the answer, and the reason it's not going to be the answer is because your equilibrium moles, the ones over here, your equilibrium moles cannot be negative moles. X could be negative. There's nothing wrong with X being negative, but the issue is that your moles cannot be negative. Your equilibrium moles, they simply cannot be negative. And if I use a negative value for X, what I'm going to get is I'm going to get a negative value for moles over here, which is going to make the whole thing wrong. वो जो दूसरा वाला ना, that I can use 0.0353. So it's going to be 0.0353 into 2. That's the moles of H. 0.1 minus 0.0353, that's also going to give me a positive value. 0.1 minus 0.0353, that will also give me a, it will also give me a positive value. ठीक है? ये clear? Is this part clear?
Yes.
Yes, sir.
अच्छा चलो, okay, moving on. ये इस पे ज़्यादा टाइम नहीं लगाना. I'm going to switch to KP now. Okay, now in KP, what you had was that you had uh, that was exactly the same. It was exactly the same as KC. The only difference was that if you have an equation like N2 plus 3H2 and it's reacting and it's in equilibrium with 2NH3, so Kc was what, NH3 concentration squared, and the whole thing, it was N2 concentration times H2 concentration cubed. The only difference was that Kp was the partial pressure or the pressure due to the NH3 gas, and that's going to be squared, divided by the pressure that's exerted by N2 times the pressure that's going to be exerted by H2, and that's going to be cubed. Okay, so that was what Kp was. So instead, because concentration and pressure for gases, and Kp was specifically for gases. Because for gases, normally you don't use the term concentration. Normally what you use is you use the term pressure. Although concentration also applies to gases, but it is a term that's often left for solutions. So you've got a gas, the more particles per unit volume you have, the more pressure it's going to have, the more collisions it's going to have. So the concentration and the pressure of a gas is directly proportional. You have a higher concentration of a gas particle, you'll have more pressure exerted by the gas. Okay, so for gases, Kp and Kc are directly proportional. You use Kp. So for example, I've got this container. It's got N2 and it's got NH3 gas, and it's got let's say the blue ones. Those are H2 gas particles. So what happens over here is that there's one extra step that needs to happen, and that is that you can only calculate the total pressure for the entire gas, right? So it's a mixture of N2 plus H2 plus ammonia gas. All of the reaction is happening, forward reaction, backward reaction, but it's all the gases are mixed in one container. So if you have 0.1 moles of N2 and you have 0.4 moles of H2 and you have 0.35 moles of NH3. That means the total pressure, let's say the total pressure is 2 atmospheres. That means the entire pressure, the total pressure is the combined pressure that's exerted by all the gases. So to calculate Kp, you would have to find the equilibrium pressure exerted by every single gas. Now, pressure of gas particles is proportional to the amount of gas it has. So if you have 0.1 moles of N2, that will, because all the gases combined are exerting 2 atmosphere pressure. So if there's a certain amount of N2 gas, it's going to exert a proportional amount of pressure. So the pressure exerted by N2 plus the pressure exerted by H2 and the pressure exerted by NH3, that's the combined pressure. 2 atmosphere is the combined pressure that's exerted by all the gases together. So there was a formula for calculating partial pressure, and that was the mole fraction or percentage times the total pressure. So iski percentage निकालो. What is the percentage? What is 0.1 divided by the total? Like if you have 0.1 and what's the total moles? That's 0.1 plus 0.4 plus 0.35, right? So if you combine all of them, so 0.1 plus 0.4 plus 0.35. So that's 0.85. So the percentage of N2 in this would be 0.1 divided by the total, which is 0.85. And that's around 11.7%. So the N2 gas fraction in the container is 11.7%. So mole fraction is you had 0.1 moles of N2 and the total moles were 0.85 moles times the total pressure. अच्छा इसके ऊपर हम फिर कल बात करते हैं. We're out of time, so we'll just cover KP quickly. We'll do some questions and then tomorrow we'll obviously start with A levels equilibria. ठीक है? चल ठीक है everyone. Take care. Allah Hafiz.